Today I am really stoked to be here giving my presentation seminar. It's been a really enjoyable past 3.5 years, and I really wanted to start off. Well, let me see if I got this myself. Really wanted to start off by acknowledging my supervisors, because I couldn't have done this without them, despite them talking about being in a back seat. I've been incredibly lucky to be supervised by Tim, Kate, Belinda, and Reece, and each of them have brought a really different perspective and a different background to this work. And I think hopefully the multidisciplinary nature of this work will shine through, and that has really come about because of the different perspectives that they've been able to bring to this work. So thank you to them. A big thank you to our project partners in Melbourne Water. As you'll see, a lot of this work is industry driven, and we're hoping to be able to apply this in practice at Melbourne Water, but also having that kind of wider impact and wider scale impact beyond just Melbourne, the Melbourne region. And I've also been really fortunate to sit in both the Waterway Ecosystem Research Group here, but also in the Optima ARC Training Centre, led by Kate in maths and stats, and hopefully that will also shine through today. So my journey, or my story, begins with stream monitoring networks. These networks provide fundamental information that we need to understand the dynamics and what's happening in our streams. Because of that, there are stream monitoring networks around the globe, in fact, on every continent on Earth, including Antarctica, would you believe? Some noticeable examples include the Chesapeake Bay watershed, the Great Barrier Reef paddock to reef monitoring program, which was in the news just today, and some of the longest data sets are in Europe, where waterway monitoring has been going back to the 1800s or beyond. These networks aim to characterize conditions, so this might be water quality, stream flow, vegetation, or values, which can be characterized as environmental values, things like water bugs, presence and abundance, platypus, given we're in Australia, fish, but also human values such as the ability to use it for recreation or water supply. But regardless of what they're monitoring or what they're targeting, they all have an aim to help support strategy, to help inspire and direct management actions, with the ultimate aim of understanding and protecting our waterways and the values that they provide to us and the environment. So the aim of my work, the kind of lofty aim, is looking to advance understanding of how we can accurately or effectively collect and accurately interpret data from these types of monitoring networks, and consequently gain new insights into stream condition, which is what I focused on, but with the overarching goal of contributing to the science so that others can take these learnings and use them elsewhere as well. So yes, Melbourne Water is a close project partner in this work, and the region has been kind of my focus area of when I've needed data to use for my work, for my study. One big advantage of this is that it is a region where we do have a lot of existing monitoring networks. Here I'm showing both the stream flow and the water quality monitoring networks for the region. Another key characteristic of this region is that it's a really diverse region. It's got gradients of different types of waterways, it's got gradients of land use, it's got gradients of climate. And those gradients allow us to interrogate potential drivers of change in our waterways, and really allow us to think about changes not just in a local context, but what might be happening globally. So it's a really nice study catchment, as well as being a really a good example of local science. So today, I'm going to go through my 4 research questions that are contributing towards this aim, and we'll finish with a bit of a summary of how this might be applied in practice. But without further ado, I'll start with sampling artifacts. This graphical up here is providing an illustration of a stream temperature process happening in the river. This is what in maths and Optima terms we would describe the grey line as the truth. This is what's happening in a stream. On the x-axis, we're looking at change over time. So this happens to be 5 years. And on the y-axis is a measure of stream temperature in Celsius. And here we're looking at how this, you can see how we've got summer increases in temperature, decreases over winter. And if we were to measure this high frequency, perhaps as we measure stream flow, this black line is what we would see. However, many monitoring networks don't have the luxury of being able to take an hourly, a 6-minute, a 15-minute snapshot. Instead, we might be looking at artifacts that are more like sampling frequencies that are more like monthly, bi-monthly, seasonally, occasionally even annually, depending on the target. That means what we see is more like what these green dots, or what these dots are showing. And the green, yellow, and purple are showing different potential strategies that we might use. But what I really want to illustrate here is that when we see this data, we don't see the black. We see the dots. And so when we have these dots and we try and apply some sort of analysis model to them, depending on how those dots are collected and how those dots are analyzed, we are possibly going to end up with an analysis or a result that differs from what is actually happening in practice. The black dashed line is the true median and trend for this black process that we showed before. And each of these scenarios, how this data was, or when this data was collected and how this data was analyzed, is potentially leading us to false conclusions. So this was my first research question, was how can historical stream temperatures, stream temperature data sets collected from long-term monitoring networks be accurately analyzed in the presence of sampling artifacts, and looking to understand this a little bit more generally as well beyond stream temperature. So for this work, I started by characterizing common sampling artifacts that are in the literature and within the Melbourne water dataset itself, looking to find some examples of the truth. One of the reasons why I looked at stream temperature was that there is the ability to collect high frequency data for that. And so I could subsample. So I used a Monte Carlo style analysis to subsample these data sets, recreating these theoretical or these sampling artifacts in a theoretical context, and then applying different analysis models that are commonly used in the literature. What I found, the key findings from here, was that, yes, indeed, like I was showing in the first kind of toy illustration, the presence of sampling artifacts and the model choices we use can lead to inaccurate and uncertain results. Not really a great story to be telling, but a cautionary tale for any of us who are looking to use these data sets and make sense of stream networks. However, there is a good news story in this, in that if we have the appropriate models in place to account for these sampling or account for the natural variability of these processes, we can accurately identify trends and site means. Now, that you can use a model to accurately identify trends and site means is not particularly groundbreaking in itself. In fact, that's why these were developed. But the key point here is that even in the presence of these sampling artifacts, which permeate through these historical data sets, this is really important because without, we can't go back and collect water that has already flown down a stream, down a river. So if we want to know what state of a river was 20 years ago, 30 years ago, we're relying upon these historical data sets to analyze them. And this work is showing that it is actually possible to do that, as long as we're paying careful attention to the sampling artifacts that are there, and that we're avoiding some of the systematic biases that can be problematic. Essentially, we just need enough information to characterize those systematic fluctuations in natural variability. So the outcome from this work was to put together some guidance notes that can be used by practitioners, whether that's in research or industry, for a set of common sampling artifacts and common uses of the data, and how that can be used in practice even when there's multiple artifacts together. And that was published in the Journal of Hydrology as well. Sorry, all of these are going to be very high level because I've got 4 questions to get through, which each could do with 20 minutes in themselves. So if you've got any questions, and I'm sure I will have missed and misexplained things, please pop them in the chat or hold your questions to the end. But along with publishing that work was instrumental in my second question, which was looking at stream temperature changes. So stream temperature itself is a key driver of ecosystem processes. It's commonly measured as part of long-term stream monitoring datasets, and because of that, it commonly is affected by these low frequency of sampling artifacts. Unfortunately, to date, despite there being widespread investigative work understanding the change of air temperature, change of sea surface temperatures under climate change, there hasn't been a lot of work done on understanding the impacts of climate change on stream temperatures. There's been a number of studies in the US, a few studies in Europe. Really, there's limited information in the Southern Hemisphere. The Melbourne water stream temperature long-term stream monitoring dataset, however, does cover a period starting in 1992. And we can see from this figure here, which is looking at changes in air and sea surface temperatures over the Australian region, produced as the State of the Climate report by CSIRO and Vaughn. We're seeing a signal in air and sea surface temperatures, and so we would expect that we would also be able to see one in stream temperature. And so the question, my second research question, was to identify if there has been a change in stream temperature in the Greater Melbourne region of South East Australia using the Melbourne water dataset, and what are the drivers of any change that has occurred. For this, we're looking at the period when Melbourne Water established this network, which is 1992, and we have 75 sites that met a criteria of having enough new sufficient information to apply the techniques that I identified in my first question. We're short on time, so I'm getting straight to results, or straight to the point. Yes, we were able to identify a 1 degree warming of mean stream temperature across the greater region over that 30-year period. This is in line with the same kind of stream warming or magnitudes of stream warming that we've seen in other regions in the northern hemisphere. It's the first time in the southern hemisphere that we've been able to quantify such a change over a long period of time. The warming occurred broadly over the region. As I was mentioning before, the variability of the Melbourne region is quite stark because of these different gradients, which gives us a really good opportunity to explore the drivers behind this. And you can see on the right-hand side, we're looking at individual sites. While there's a broad scale warming, we do have significant variability among sites. That provided me with the motivation and the opportunity to interrogate what was the potential drivers of these changes. I did that using a random forest model, trained using the key drivers, the known key drivers of stream temperature, and using Gini index to understand their relative role, their relative importance in predicting those changes in stream temperature. And two of the key drivers that shone through were changes in air temperature, as can be expected and has been shown in other studies. There's a high link between air temperature, a strong link between air temperature and river temperature, but also that urbanisation is playing a role there as well. This can be illustrated by examining those gradients of air temperature and urbanisation across the region. So I would love a bit more time to get to explain this figure, but I will do my best. The symbols represent the stream temperature change. So a triangle pointing upwards is an increase in stream temperature. A triangle pointing downwards is a decrease in stream temperature. A circle is a non-significant change. The size of the symbols indicates the magnitude of the change. So you can see in this northwest of the region, we're getting some really strong changes. In the middle, it's kind of petering out a little bit, and we've seen these cooling in the southwest. Now, the left-hand panel is showing the change of air temperature shown as a colour. There was broad-scale warming across our region, but there was more warming in the northwest, less warming in the southeast. And this really corresponded, this gradient corresponded to this change in this, alongside this gradient of changing in stream temperature. And the areas in the center here where the gradient of air temperature change was not as great, change in stream temperature could really be explained by also the presence of urbanization in those catchments. And this is really the Dandenong catchment and the centre Melbourne area here where there is a strong level of urbanisation that has essentially compounded the air temperature changes. And this work we published in Water Research with a real focus of further investigation on the roles of climate change and urbanisation. Okay. Following stream temperature, I then turned my attention onto stream flow and the prediction of stream flow at ungauged reaches. So this prediction of stream flow at ungauged reaches or ungauged basins is one of the key questions of hydrology. Indeed, this has been a question that we've been wanting to answer at Melbourne Water for quite some time. The reason why it is such a key question that occurs globally is that even in a region like Melbourne, where we have a high number of stream gauging stations, they're the magenta squares shown on this slide, we have 114 gauging stations for 25,000 kilometres of waterway. That means there are orders of magnitude of reaches that don't have any form of stream monitoring on them. And in order to understand the impact that changes in stream flow or that hydrology might have on the values in those reaches, we need to be able to take the data from where we observe it and interpolate it to where we don't. This is also an important factor in analysing water quality, and you'll see that in the Melbourne region, and again, this is repeated globally, the water quality monitoring network for the region is not co-located in many places, in fact, in the majority of sites with stream flow. And so if we want to analyse our flow affected variables, such as total suspended solids or nutrients, we need an estimate of stream flow. So this was the motivation behind my question 3, which is stream flow, making predictions of stream flow at ungauged reaches. Under what conditions are modelling techniques able to accurately estimate daily stream flow for ungauged sites? It's really kind of a stress test or an investigation of different approaches. And can we predict, based on their characteristics, the algorithms that are best suited to make predictions at locations that don't have stream monitoring? Again, we're using data from 1992 to 2024. And we're using two different types of statistical models, very contrasting styles or models. The first is a geostatistical model. For those calling in from Optima, you will be aware of kriging, universal kriging. The spatial stream network model is a form of universal kriging that is adapted for stream networks, specifically for the directional and nested directional flow structure of stream monitoring networks, where Euclidean distance or straight line distance might not be the best explanatory variable. For those of you not from Optima, geostatistics models work by basically borrowing information from the nearby sites. If you're at a bottom site at the bottom of a catchment, you look upstream and you say, hey, where do I have some sites that provide me with information? And it works out how much to borrow information or how much to use information from those upstream sites. The contrasting algorithm that I used was a machine learning long short-term memory model. This is a pattern recognition model. We chuck as much information into training this data set. AI is big in the news these days, and everybody knows or has heard about how much data is used to train AI. This is another form of AI, but we're using it for pattern recognition for stream flow. So we're giving it a heap of data, and it is going to learn those patterns and repeat those patterns in making predictions. And then the technique I used a meta modeling technique known as instance space analysis. A big shout out to Kate and Andreas at Optima, who were integral in developing instance space analysis. It's a model that's used to test the suitability of algorithms for particular instances. In this case, for different reaches or locations across a stream network. And this is the first time that it's been used in a hydrological context, and is used to essentially understand or predict a best algorithm for a particular location, and predict confidence associated with outputs for those locations. I'll very, very quickly give a bit of an explanation as to how it works. We start off in our physical realm, our physical space, with our stream network. So it's on our right-hand side, our spatial network. That physical network is then mapped into an instance space. It's very similar or analogous to a principal component analysis, where we're looking to define key features that can define these sites and separate them in a two-dimensional space. We can then use a classifier or train a classifier on the observations that we have to understand, in these scenarios, this model performed better than that scenario. And then we can use this trained machine learning, in this case, it's a support vector machine algorithm, to then predict within that instance space and then translate that instance space back into reality. So yes, it is a model of models, but we do have a basis for it in physics.
Very good question. Which of those two colours corresponds to which of your two models?
So the pink or the magenta is corresponding to the geostatistics, the spatial stream network model, and the green to the LSTM, the machine learning model. And I'll hopefully be able to answer more about that here. So the results for this study were overwhelmingly positive. We had some really good results come through. Both of these models, the LSTM and the spatial stream network model, were shown to be really highly effective at making predictions at ungauged reaches. On the left, I have on the y-axis, we're showing model performance using KGE. It's similar to Nash-Sutcliffe efficiency, where a prediction of 1 is perfect prediction. When we get starting to get below 0.39 is our threshold for good performance, or benchmark for good performance. Once we're starting to get below 0, we're starting to look into the realms of poor performance. On the right-hand side, we're looking at individual. So the x-axis in this case is that same KGE score, and on the y-axis we have individual sites. The shapes correspond to prediction or performance of different models at those sites. The key takeaway from the right-hand side here is a large amount of variability. So even though we've got, the 25th percentile is above our threshold for good for both of these models, we're still seeing, in particular for the spatial stream network model, some really erroneous results, some really poor results that we would want to try and avoid if we can. And that's where instance space analysis really came into its fore. It accurately predicted, I think it was 91% of accuracy of accurately predicting the correct model to use for a particular location. And when it was wrong, the mean penalty for an incorrect selection was much smaller than the mean advantage for correctly selecting the correct algorithm for a site. And what this really did is it's shown here in blue in the middle here. It really bumped up the median performance, but the key for me really is that it drags up this tail. It's really avoiding a lot of these really poor performing situations here. And we were able to further explore this by benchmarking not against each other, but benchmarking against those predictions of poor or acceptable and or good performance, and then predicting that across the region. So the key takeaways here, our LSTM model, our machine learning, our pattern recognition had really good, consistently good ability to make predictions across the catchment. Our spatial stream network model, our geostatistical model, while not as consistently good, when it was good, it was better than the LSTM model, the pattern recognition model. The circumstances that led to that, and this was where instance space was really good for being able to interrogate the drivers behind this performance, were locations where there was a high density of sampling. This kind of makes sense. When we have a lot of data to draw on, this model is able to say, hey, I can see 4 or 5 different gauges upstream. I'm going to use that information in a way that makes sense. When we're out in the outer catchments where we have a sparser set of sampling, it really doesn't have that data to rely upon. So it's kind of flying blind and going back to its kind of baseline state, its mean state. The other area where it really excels is where there is a break between the relationship in the catchment and stream flow. So for example, if we have a major dam structure, if we have some kind of diversion, our pattern recognition model will see a great big catchment ahead of it. Our spatial stream network model is seeing that 95% of that water is being diverted for agriculture, and the stream is now only seeing 5% of that, if there is a gauge there for it to draw upon. And so this work was published in the Journal of Hydrology, but going alongside that are now predictions of stream flow across the Melbourne region, which will be useful, hopefully for many people in this group as we continue to interrogate and understand what's happening in the Melbourne region. But from personal note, looking at stream water quality, we will now have stream flow estimates to accompany our water quality measurements, so we can start to address that sampling artifact when we're analysing these low frequency data from the water quality network. Okay, on to my final question. So my final focus for my PhD was looking at optimization and adaptive management. In question 3, I investigated how to construct a model based off the data sets that were available to us from the region. In this question, I'm looking at how can we modify the data sets for the region in order to support our modeling. And in doing that, so can we optimize the placement of our samples that we take? In doing so, can we use information about that to change or manage the way that we collect data in a way that avoids creating sampling artifacts that we don't want to see in the data set? In particular, things like these missing data points. So my fourth and final research question was looking at how can existing stream monitoring networks be optimized and effectively adapted to changing circumstances so that they continue to provide useful data over the time periods that they are operating. Now, this was, or 3 kind of key actions were identified to support this aim. First is the idea of reducing the number of sites within a monitoring network while limiting the impact on model performance. That might be eliminating so-called redundant sites, or it might be, as would face stream network managers face worldwide, somebody saying, hey, overnight your budget has been cut in half. How can we minimize the damage? A less common occurrence, but still one that does occur, is the situation when someone says, hey, your budget overnight has doubled. And that was the other action that the second action that we're looking to here. How can we effectively acquire additional sites to improve model performance? More likely, we could combine those 2 things and say, can we identify sites that aren't providing us a huge amount of information and move them elsewhere, adapt our monitoring network within the same amount of budget that we have? And can this process provide us with information to prioritize responses to sampling disruption so that we can continue to effectively collect data? The key tenet of this work was the integration of network design and modeling. So in question 3, I spoke about how we had this data set and we built a model based off that to make predictions. However, for a set budget, where those sites are located can influence the prediction performance of that model. So the addition or the removal of sites will affect how well that model trains and how well that model predicts. And so, therefore, for a given budget, there does exist an optimal network that maximizes the performance of our model. And that was really the key tenet that I was working to behind here for this identifying potentially redundant sites or acquiring new sites. I built a again, a geostatistical model, a spatial stream network model. There was a particular reason for using geostatistics in that not only does it provide an estimate that we can use to characterize accuracy, geostatistics provides a measure called Kriging variance, which is a measure of the uncertainty of predictions that's spatially varying depending on where you are in the catchment. And therefore, we can use this model of uncertainty as a optimality criteria. Because we've got our optimization audience here, I'll delve into this a little bit deeper. We used a greedy exchange algorithm to find optimal designs. A greedy exchange is a potential solution for optimal solutions for combinatorial optimization problems. Kind of similar to knapsack problems in general. This greedy exchange process commences with an initial network for the budget that you're seeking. So say you have a budget of 50 or 100 sites, we create an initial network for that site, and we create a set of candidate sites. So for this initial site, we then look to make an exchange of sites. We look at, can we remove one site and replace it with one site from our set of candidate sites? And we go through that process until we find a solution that improves our model fit. And we keep repeating that process until we get to the point where no exchange of our set of new sites improves our model fit. And that's our locally optimal design. This process is extremely fast, especially compared to a full exhaustive search of all combinations. However, it can get stuck in local minima or maxima, which we deal with by having multiple random restarts of our initial network. And from that, we can identify a network that has an optimal network. The key takeaways from here is that this process was effective. Depending on the optimality criteria that we were judging our network by, and depending on the optimality criteria that was used in the greedy exchange, we could effectively find subsets of a network. So this on the x-axis is showing the number of sites within a network, and on the y-axis is showing a degradation in performance relative to having all of these sites at point at 89, a network of 89 sites. And as we can effectively use this process to effectively remove sites from that network with minimal impact. However, there is a rather large caution here that says that using a single measure of optimality isn't going to mean that your optimal network is optimal across all uses. And so it was found, this figure here is illustrating the differences in performance when measured using accuracy, which is p-optimality, or uncertainty, which is k-optimality, and how they can differ. So without getting into that too much further, which is what I do in the paper, it was a word of caution to use multiple measures of optimality when assessing what is a truly optimal network. Regardless, this first line of the table, I'm showing how we can reduce a theoretical network of 89 sites down to 66 sites with no change in optimality of p-optimality, which is our error, or other measures, d-optimality or k-optimality. While there was a little bit of degradation in those, the next step of this process was to then acquire new sites. And we could repeat this process using Kriging variance as a measure of uncertainty, minimizing the uncertainty over the catchment, and in doing so, bringing our total number of sites back up to 89 sites, we dramatically reduced our prediction error. In fact, it was less than 50% of our original network. And we could also improve d-optimality and k-optimality despite the slight degradation of it when we initially removed those sites. The discussion of this deserves far more attention than I can give now. And so if nobody has understood what I've said, I will not take that as any form of criticism. And I'm very happy to talk about this later on. But in effect, what this looks like is that we can remove sites or effectively identify sites and provide limited information in an existing stream network. We do that because these observations already exist, which allow us to train a model. And then we can use those models to predict where we would be able to best acquire new sites, effectively reducing our prediction error, and for the same budget, more efficiently collecting information and collecting data. We can also use this information by taking this analysis of the data set all the way down to, say, 1 or 2 sites to identify which sites are still present at those really low budgets. When we do that, we're effectively identifying sites that provide us with a large amount of information and are a larger priority to maintain sampling at. So the sites that are appearing up towards the end of our optimal budgets, they are likely not providing us with a huge amount of information. The sites that when we are looking at, this, say, worst case budget cuts of saying you've got 10% of your current budget, when we're looking down that low, those sites there are the ones that are providing us with key information that provides us a lot of information about large areas. And we can use the budgets or the information about when they become important to effectively prioritize our management actions. These are the sort of sites that we want to be getting out there and restoring sampling at straight away after some kind of flood damage. Of these sort of sites where we might want to prioritize for high frequency sampling or further investigations, because they're going to provide us with more information about the catchment than others. And this work we, as Belinda mentioned, we submitted to Water Research earlier this week. Okay, so that was a very short description of a lot of work, and I hope some of it was at least coherent. Overall, my aim, was to advance understanding of how to effectively collect and accurately interpret data from stream monitoring networks and gain new insights. To do this, I looked at the impact of sampling artifacts, how data is collected, and how we can accurately analyze our historical data sets. I applied the findings from that to investigate stream temperature changes over the Melbourne region, identifying a 1-degree warming that has already occurred since 1992 to now in our streams, and that varies spatially across the catchment, driven by urbanisation and changes in air temperature. I then turned my attention to stream flow, looking at how we can make predictions of stream flow at ungauged reaches, and the methodology there for interrogating models that are best suited for particular regions or reaches, and noting that this methodology is also likely to be applied to other parameters, for instance, water quality. And finally, investigated the optimization and adaptive management of these networks, how we can integrate our data collection and our modeling together to improve both. Future work from here. I'm hoping, or I've aimed to set a strong foundation, theoretical foundation that we can continue on with at Melbourne Water and apply at Melbourne Water and in this research group. The ultimate aim is to take our long-term water quality monitoring network and develop targets that we can use in strategy, that we can use to identify suitable management actions and apply them as part of the healthy waterway strategy. So that is the lofty target we're working to with that. There is a lot of kind of similar or repeating the analysis that I've gone through today to get to there. And on the adaptive management side of things, the methodology is still kind of in its infancy, extending this methodology to different parameters, to examining multiple parameters and multi-objectives, and how they might fit together in some kind of framework is an obvious next step to keep exploring. But while I'm here, I also want to note a large number of other collaborations that I've been able to get involved in while I've been doing my PhD. And I'm really glad that I've got a little bit of time to call out these people and thank them, because it's really rounded out my PhD experience. Working in a team and working across multiple different areas has been really rewarding. A big shout out to all the people I've been involved in water quality trends, stream temperature trends, to the Monash Water Quality Group, hello, on headwater streams. Big thank you to the Seuss 7 team there. It was a really rewarding project. Street trees and wetlands. Chris, I really appreciate working together on continuing to work on, in particular, on street trees with you. Water quality monitoring with the ModSim Special Interest Group. Geostatistics for Alan with a heap of advice and conversations about geostatistics. And I was also fortunate enough to be a member of the Melbourne Centre for Data Science Doctoral Academy during my time here, which was really, really rewarding. But my biggest thank you is to Tim, Kate, Belinda, and Reese. This has been a really lovely journey to work with you for the past 4 years. I feel really privileged to have worked with you, to spend so much time talking about all sorts of things, water quality, modelling, stream related, life related. I'm really privileged to be supervised by you and to call you friends. So thank you. And a final thank you to Work, to Optima, to Melbourne Water, everyone there, and Mick as my chair. Thank you for coming along. Thank you for being part of this journey. It wouldn't have happened without you.